All right, y'all, we are getting down to the nitty gritty. Here we go. Unit 7, Lesson 4, the area between two curves. What we're going to learn today is how you can use a definite integral to find not just the area between a curve and the x-axis, but also between any two curves that you can imagine. And so we're going to start off, right? I've got this graph here. It's a graph of the function negative 1/2 x squared minus 2x plus 4. And first things first, I'm just going to find and illustrate the value of the definite integral from -5 to 0 of f of x. Okay, well, what we need to do here, right, if we use the fundamental theorem of calculus, because what I really want to find, right, what I'm trying to find is this area here. And because it's curved, right, I can't actually use geometry to find this area. Geometry is not going to be good enough to find this area. So what I need to do is I need to do the fundamental theorem of calculus, which would tell me that the definite integral from -5 to 0 of -1/2 x squared minus 2x plus 4. And again, I've done this all out ahead of time, so I'm going to be doing this, a little bit faster here because the antiderivative stuff is not what we're working on today. But we take the antiderivative, right, which would be equal to -1/6 x to the third, right? You can kind of follow along by taking the derivatives backwards. I'll do that with a dashed line to check. -1/6 x to the third. This one's a little easier. This is going to be minus x squared and plus 4x. Right, so these are all the antiderivatives here. You can check with their derivatives going backwards. And the fundamental theorem of calculus says I should be able to plug in 0, plug in -5, subtract those. And so what we have here is, well, plugging in 0, this whole first one is just 0. And then we're going to subtract, and this is going to be, a whole bunch of funky math here. This would be calculator active, where you would just leave it like this, -1/6 times -5 to the third minus -5 squared plus 4 times -5. At this point, you're just going to trust me and you're going to say, okay, yes, this is 24.167. And I don't know, yeah, that looks reasonable. Like if it was a full square here, if I did that full rectangle from 5 to 6, it'd be 30, and we chop off a little bit. Yeah, 24.167 sounds good. So now on this same graph, right, I'm going to graph the function 1/2 x plus 4. And so it has a y-intercept of 4, a slope of up 1/2. So let me repeat that a few times just to get, ooh, this is a little tricky here with all these up 1/2, up 1/2, up 1/2. Yeah, that looks pretty good there. So let me go ahead and draw this line the best that I can. Nailed it. And so let's imagine here that I wanted to find the area under this curve. And you can probably see where this is going. And so I'll do this one horizontally so we can see what's going on here. So I'm going to find the area between this curve and the x-axis on this same interval from -5 to 0. And so we do the same thing here. We find the definite integral from -5 to 0 of 1/2 x plus 4 with respect to x. This will be equal to, right, 1/4 x squared plus 4x. Same thing, calculating it from 0 to -5. What this will be here is this will be, of course, 0 minus 1/4 of -5 squared, so 1/4 of 25, we're in decimal land, plus 4 times -5. And so what we wind up with here is actually 13.75. And so that makes sense. It's less than 24.167. And so this one, I think it's just kind of intuitive, right? What you can do now, if I found this entire green area and I found the entire purple area, well, this right here is the area, right? If I find the area between these two curves right here, that region, maybe I'll do like polka dots here. Ooh, a watermelon. It's kind of a backwards watermelon. If I subtract what was going on the first definite integral minus the second one. That gets me the area between these two curves. So all I would have to do here, right, to find the area of the watermelon region is I would find the definite integral from -5 to 0 of, I'll call this f, and it was called f and g, of f of x minus g of x, right? And this is the same thing as saying them both separately, is 24.167 minus 13.75. And this is equal to 10.417. And so that's mostly the lesson today, right? There's some additional difficulties where, like, you know, maybe I don't tell you what these two intersection points are, and you have to find those intersection points on your own. But other than that, that's the key point here. You can find the area between two curves by finding the definite integral of their functions subtracted. So I'll leave that up there for a second here. Okay, let's do one more example. You know what? This next part, I don't really think it's worth the time here. What this was going to show is if you do it all in a single definite integral, right? If you like actually combined these things into one, so you did -1/2 x squared minus 2x plus 4, and before you even took the definite integral, you subtracted this one, and so you'd have the definite integral of -5 to 0 of -1/2 x squared minus 5 over 2x when you combine these two things. I guess it does make it a little bit easier here. What it turns out is that, and this is equal to, yeah, okay, I guess I'm ending up doing it, -1/6 x to the third minus 5 over 4x squared. It turns out that this is the exact same thing if you did the subtraction first. And I'll leave that as an exercise to you if you're interested. But it tells us that the general way we find the area between two curves, so the area between f of x and g of x is the definite integral from a to b of f of x minus g of x with respect to x, where x equals a and x equals b are points of intersection. And same rule here, you want to go left to right or you're going to get this backwards. So A needs to be the intersection point on the left, B needs to be the intersection point on the right. And so let's just focus in. Let's just do like one more of these here, maybe a little bit of a trickier one. Let's find the area of this weird region R. Okay, now they actually haven't labeled these for us, so we do have to kind of do a little bit of investigation and think to ourselves, okay, which one of these is, let's call this one F and this one G. We do have to do a little bit of investigation to figure this out. And to me, the first thing that jumps out is, okay, I'm like, okay, which one of these, when x is 1, gives me 0? And if I plug in 1, f would be the sign of pi, which would be 0. So that makes sense there. So we got f on top of g. And so let's go ahead and let's say the area of R is equal to the definite integral from 0 to 2, because that's the intersection points of the sine of pi times x minus the definite integral from 0 to 2 of x to the third minus 4x. Now, sometimes, I forgot my dx's, sometimes it'll be easier to combine these in advance, sometimes it won't. Here, I think it's easier to just combine these after the fact. And so first things first here, right, we need to take our antiderivatives. And so this is kind of a guess and check one. I think to myself, okay, what thing, when I take its antiderivative, would give me the sine of pi x? And the first thing I think of is, oh, this is easy. It's the cosine of pi times x. But then I'm a good calculus student, so I always check my answer by retaking the derivative. And I remember that if I go, and I'll do this over on the side, if I go to take the derivative of the cosine of pi x, Well, two things are happening here. Number one, the derivative of cosine is negative sine, so I got to deal with that negative sign, but also the chain rule times pi. So I need to throw in here, and I'm going to go ahead and I'm going to make myself a little bit more room here. I need to throw in here a negative 1 over pi. So it's negative 1 over pi times the cosine of pi x. I'm going to do that from 0 to 2. If you were really paranoid, you could check that derivative again. And then we're going to have minus, this one's a little easier, the antiderivative of x to the third, 1/4 x to the fourth, minus, and this will be 2x squared, all again from 0 to 2, all from 0 to 2. Now, we can go ahead and we can plug all of this in. So I'm going to do this as like negative 1 over pi times the cosine of 2 pi minus, and I like to use brackets inside brackets, minus negative 1 over pi times the cosine of 0, and we plug in 0. All of that minus, I'm going to need this room back here, sorry, cosine of pi, all of that minus 1/4 times 2 to the fourth minus 2 times 2 squared, holy cow, minus, all in brackets, 1/4 times 0 to the fourth, minus, I could have just put in 0 here, all of that. Now, I'm going to give you a fun hint here. If this is a free response question, you stop right there because we've got all numbers left here. There's like almost nothing left to do here, okay? And so let's just kind of work this out though. Again, I would circle my answer. Well, this part is 0. That makes things a little bit easier. 1/4 times 2 to the fourth. Okay, so this is going to be 2 to the fourth is 16. 1/4 of that is 4. Okay, so this is, I'm going to put a little note here, 4. 2 squared is 4 times negative 2 is negative 8. Okay, so this is going to be 8. And so 4 minus 8, this is going to be minus negative 4 in the end here. Okay, so that's going to be minus negative 4. All right, so it's going to work out to be a plus 4. Now on the left here, what we have here is actually fairly interesting. The cosine of 2 pi, right? Think about your unit circle. 0, pi over 2, pi, 3 pi over 2, 2 pi. 2 pi and 0 are both right here, and they're both equal to 1. So we're going to have negative 1 over pi minus, this is the cosine of 0. It's the same thing. So minus negative 1 over pi. These things will cancel. What we're going to have here is 0 minus negative 4. The answer here is just positive 4. So that's fun. The area of this entire thing, even though it's these two kind of kooky equations, the area of this whole thing is just is just 4. So that's fun. This is the area between two curves. Good luck on this. Get this delta math done. And on the summative assignment, it's, I would say, 80% this and 20%, if not less, of what we're doing on Thursday. So you can get a good jump on the summative.